Okay. So the problem is cosine 2x equals root 3 over 2. Really what makes this problem different is the fact that you have a 2x instead of just an x. So what I'd like for you to do, instead of looking at as 2x, just look at it as like a u. We're just going to make like a substitution. And so we're saying cosine of what angle u gives us root 3 over 2. So you go to your unit circle, right, which you've got. And when you say cosine, you're referring to the x-coordinate, correct? So where on your unit circle is your x-coordinate root 3 over 2? It's going to happen at x-coordinate. So at pi over 6, and also at 11 pi over 6. So those are the two angles. Well, the angle goes all the way around here. Those are the two angles. That's terrible pi. Those are the two angles where if you let u be equal to those, you would get the answer, right? But unfortunately, because it's a 2x, you can't just set 2x equal to those two angles. It's more complicated than that. So what we're going to do is we're going to find a general solution first. Now let me explain what general solution means. What we're going to do is we're going to look at, let's focus all of our attention on just this particular angle right here, pi over 6. Pi over 6, that angle in the first quadrant, there's an infinite number of angles that are equivalent to pi over 6. Like I could take pi over 6 and I could add one complete rotation. So I could go and say, go around one more time, right? So I could add 2 pi to that. Or I could have said, why don't I go around, instead of going around one time, why don't I go around 2 times? And I'd still be at the same angle, right? So couldn't I go around as many times as I want? So go to pi over 6 and then just go around as many times. So what we do is we put pi over 6 plus 2 pi k, or you can use n. And k and n is basically the number of rotations. So you could have k be 0. It could be 1. It could be 2. It could be 3. It could be any of those. And you could also have -1, -2, -3. So you could go backwards. Instead of going counterclockwise, you can go clockwise. Does that make sense? So what we have, that's our general solution. If our u is equal to any of those angles, we will have the correct answer. We will have square root of 3 over 2. Does that make sense? Okay, now we're not done because we need to come back in here. We need to replace u with 2x. So what we have is 2x must be equal to pi over 6 plus 2 pi k. And then we have to divide everything through by 2 to get x. So when I divide pi over 6 by 2, I get pi over 12. And when I divide 2 pi k by 2, I get pi k. All right. Now, that's just the pi over 6. Now we have to look at 11 pi over 6, which was that other angle. So these are involved. I mean, these problems take a little bit of time. We're still not even to our answer yet, because we're only supposed to be finding the answers to this in the interval 0 to pi. Okay, so far here's where I am, but I still have not addressed the issue of the answers just between 0 and 2 pi. Okay, let me now take the 11 pi over 6 and let's do the same idea. You could go to 11 pi over 6, you could add a rotation or 2 rotations or 3 rotations. So what we'd be saying here is that the u, the angle, must be 11 pi over 6 plus, again, 2 pi times some number of revolutions. And then replace again my u with 2x. Is that all right? Okay. and then divide through by 2 again. And so you get 11 pi over 12 plus pi k. All right, so that's my second general solutions. So just keep in mind what these two things boxed mean. It means if x is any of these angles or any of those angles, any of them, we will satisfy the original problem that cosine of 2 times x is equal to root 3 over 2. That will be satisfied. But now we want to say, let's just look at the angles in 0 to 2 pi. So just those. So here's how we would do that. All right, so here's how we would do that. I'm going to start plugging in values of k. So I'm going to take that first box here, and I'm going to let, first of all, k be 0. If k is 0, what would we get for x? It would just kill off the pi, so just pi over 12. Do you agree? And that does live in the interval 0 to pi, right? That's inside that interval, because pi divided by 12 is smaller than pi, and we can go all the way out to actually 2 pi. So that's all right? Now let's do k equals 1. If k is 1, x equals pi over 12 plus pi. You see where that comes from? Replacing the k with a 1. And so now you have to get a common denominator. Pi over 12 plus 12 pi over 12. So I'm just rewriting pi as 12 pi over 12. And now you can add the two together. You should get 13 pi over 12, right? The question is this inside the interval 0 to pi? So the easiest way to do this is just to look at, forget the pi, just look at the number in front, 13 divided by 12. That's got to be smaller than 2 to be inside that interval. And 13 divided by 12 is smaller than 2. Agreed? So that's going to work also. So this is a correct answer. And we keep doing this. We keep doing this until we get outside of 2 pi. So now I need to let k be 2. So pi over 12 plus this time 2 pi, and common denominator again, and it becomes somewhat tedious here, if you didn't already agree it was. So multiply top and bottom by 12, you get 24 pi over 12. Add them together, 25 pi over 12. And now 25 divided by 12 is bigger than 2, right? Because 24 divided by 12 is 2, so 25, it's a little bit bigger than 2. So because that's bigger, we chunk this, and that means we can stop. And so the only two answers we have so far are x is pi over 12 and x is 3 pi over 12. Now that's what we got here. Now we have to go and we have to do this one. Same story. So I'm going to start by k being 0, and I get my 11 pi over 12 right away. That's definitely smaller than 2 pi, so I'm okay with that. K equals 1. So if I do that, I'm going to get 11. X equals 11 pi over 12 plus, I'm turning k to 1 here, so plus pi, which is 11 pi over 12 plus 12 pi over 12, 23 pi over 12. That's smaller than 2 pi, right? Because that's smaller than 2. So this one works. So I've got that answer now. And I had the 11 pi over 12. And if I try k is 2, it's not going to work. Check it for yourself. Yeah, we won't do it. Okay, so that's it. It's pretty exhaustive if you look at it all back up. I mean, you have to, whenever what's inside the whatever. Let me back. Whatever is inside this trig function, if it's something other than just x, like 2x or 1/2 x, we've got to set up a general solution, and then we have to sit there and try these different values of k. So let's do another one. I'll just start a new page here. Which one do you want? That one? Okay. So let's say we have cosecant of 2x equals 1/2. Now, first of all, I don't like cosecant. Well, I like it, but I'm going to act like I don't. And I'm going to rewrite it as 1 over sine 2x equals 1/2. Right? Now, I'm going to multiply both sides by sine 2x, sine 2x, to try and get my sine out of the denominator. It'll cancel on the left, and it'll appear on the right. And then I'm going to go one step further. I'm going to try and get the sine 2x by itself. I'm going to multiply both sides by 2. Well, I can put it in front here. 2 here, 2 here. So you get 2 equals sine 2x. And right here at this point, major alarm bells should go off, because no matter what is inside sine, we know that any sine function, as long as it hasn't been moved up or down or changed in any way, any basic sine function, sine of x, let's say, looks like this. And it's bounded between 1 and -1. So if I have sine here of something, and it really doesn't matter what it is, I know that the answer has to be between -1 and 1. But it's saying, trying to figure out where it's 2. It's not ever going to happen. Right? So there's no solution here, since you could write this down. I mean, you don't need to write all this, but here's why. Because sine of 2x is got to be between -1 and 1. Right? So there's no way it could ever achieve 2. Now, had this side on the left been 1/2, we would have been in business. We would have been working this problem further. So we're done. Try another one. That one was too easy. Now here, this is a good one. Tangent 2x equals √3/3. All right, so again, we're going to just forget about this right here, the 2x. We're just going to make sure, we're going to call that u maybe later. It doesn't matter. It's not relevant at this point. What's relevant is we want to know when tangent of something is √3/3. So remember again on our unit circle, tangent of some angle, I'll call it theta, is the y-coordinate. The y-coordinate divided by the x-coordinate. So we're wondering, when are we going to get a √3/3? Well, nowhere on our unit circle is our y-coordinate exactly √3, and nowhere on our unit circle is our x-coordinate exactly 3. But if we look around, which y-coordinate has a square root of 3 in it? Let's see, at y-coordinate, how about pi/3? So let's just mess with this one. Let's see what would happen. That's 1/2 √3/2. Let's just try taking the y-coordinate and dividing it by the x. It would have been, I'll do it up here, √3/2 over 1/2, right? That's the y divided by the x. Now, division of a fraction is the same as taking it and flipping it and multiplying like this. So division is the same as multiplication of the reciprocal. These two cancel, and you get just √3. No good. because we need root 3 over 3. So it's not that one. So let's try something else. Is there somewhere else where we have root 3? Well, you know what? Yeah, we have it on that one. Let's try this angle here. And this one was root 3 over 2, 1/2. Now I'm going to kind of do that over here because I'm out of room. I take the y coordinate, 1/2, and I divide it by root 3 over 2. And then that's the same as, remember, flipping. So I'm going to cancel this and flip it, bring it up here. It'll be 2 over root 3, which cancels out the 2's. And I'm left with just 1 over root 3, which still isn't what I want. However, I can rationalize by multiplying top and bottom by root 3, and that gives me 1 times root 3 on top, and then root 3 on the bottom is 3. That's what I wanted. So it worked at this point here, which is the point, well, what's the angle? I guess that's the more important thing. What is the angle here? Pi over 6. But is that the only place on the unit circle where I get that to happen? Yeah. Well, we want our x coordinate to still be a root 3 over 2. We want our y to be a 1/2, but they can both have the same sign, and they can be positive. In other words, if we go directly across this point here, negative root 3 over 2, and then negative 1/2. Do you see that if you set that up the same way? Set that up the same way. Okay. Then you take the y coordinate. So I'm doing this one now. Take the y coordinate is negative 1/2 divided by the x coordinate is negative root 3 over 2. It's the same exact problem because the negative over negative is positive. So because these are going to be gone, it's essentially the same problem as that. Do you see that? Okay, those two are going to be gone, negatives. So you get the same result. All right, so here's what we've got now. We know that, if I go back to this circle, we know that the two angles that we get tangent to be root 3 over 3 is here, and then directly across from it, here. So it was at pi over 6, and at, what was the other angle, 7 pi over 6, all right? Now, what you don't want to get caught up in is you don't want to be like, oh, okay, every time I have one of these problems, I'm always going to have 2 places it happens. It could be 1, it could be none, it could be 3, it could be 4, it could be 6. There's so many different variations that you don't want to just be like always like, oh, I'm looking for 2. That's all. The reason I'm stopping is because there's no other way I'm going to get the root 3 over 3 to happen unless I have a root 3 over 2, 1/2, either both positive or both negative, because it's got to come out tangent. They're saying here they need our answer to be a positive number, so they either both have to be positive or both negative. So I've found both angles, or yeah, both points on the unit circle. There's no others that I'll be able to come up with. Okay, now we need general solutions. So here's where we're going to have to think through this. This is a little different than the first one we did. Remember on the first one we said, what's this angle? Pi over 6. And then we said we could add a full rotation and come back to it. So we could just add 2 pi, add 2 pi. Well, watch this. This one actually lends itself to something even more natural. I can get, if I start at pi over 6, I can add a half rotation and be at the other angle. And then another half rotation and be back here. And then another half, and then another half, and then another half. And I'm kind of killing 2 birds with 1 stone. Instead of looking at it as 2 separate answers, it's the same answer. It's pi over 6 plus any half rotation. Now, full rotation is 2 pi, right? Full rotation is 2 pi. So a half rotation is pi, and then k. And remember, I said you could use n instead of k. Sometimes the books use n. So this is what our angle needs to be. Now, what was our angle? Let's go back up here. What was the angle inside of our tangent function? We had called it u, right? But what was u? 2x, right? So I'm going to come down here and say that my 2x has to be equal to that. Now, it's critical that you see that this covers everything because of the half rotations, you're picking up both of those points every single time. So as I add a k, I just keep going around half, 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 and I get all possible combinations. Yeah? Okay. Now what we'll do, we'll divide through by 2 again. Pi over 12 plus, now we're going to get pi k over 2. And you remember how before we were letting k be 0, then k be 1, then k be 2, and k be 3? Oh yeah, what was the interval? I never looked on this problem. Did they give us an interval? Yeah, still 0, 2 pi. Sorry, I forgot to put that up here. We want to look between 0 and 2 pi. And so when I'm looking at this, I could start letting k cycle through right now. But there's something you can do to kind of eliminate having to get common denominator every single time you do a k, and that's get a common denominator now. So what I'm going to do is I'm going to take this, I'm going to turn that 2 down here into a 12 by multiplying top and bottom by 6. So I get plus 6 pi k over 12, and then pi plus 6 pi k. I cannot combine those together because they don't both have a k in them. Wait a minute, hold on. I don't know why I wrote 16 here. You see that? I don't know why I did that. 16. It's a 12. So now they have the same denominator. That makes sense? Okay. You'll see now, if I put that common denominator first before I start letting my k's cycle, it's so much cleaner. So look, k is equal to 0. Let's start there. If k is 0, we kill this entire term off, and you just get pi over 12. Now let k be 1. If k is 1, that's a pi plus 6 pi, isn't it? So that's 7 pi over 12. See how much cleaner that is to do it that way? And then let k be 2. Oh, I haven't even been checking. We need to make sure these are all within 2 pi, which they are so far. Let k be 2, and you should get pi plus 12 pi, 13 pi over 12. And you can keep going, or you can kind of notice a pattern here. The numerator keeps going up by 6, and that's kind of because we're going by 6 each time. So the next one, without even looking, should be 19 pi over 12. Is that still within 2 pi? Yeah, because 19 divided by 12 is still less than 2. So the next one should be 6 more than that. So what, 25 pi over 12? But that one doesn't work because 25 pi over 12 is bigger than 2, so that's not going to work. So we have 4 solutions. Pi over 12, 7 pi over 12, 13 pi over 12, 19 pi over 12. And that's pretty much it. Yeah. Oh, it's all right. Getting help? What?
Yeah.
Yeah. Okay, so we're going to work, this is number 8, right? Number 8. So this one looks pretty intimidating, but it's the same process. I'm going to divide both sides by 2. And so I have cosine of 2x plus pi over 4 equals root 2 over 2. And I keep forgetting to put this darn thing here. They want all the solutions between 0 and 2 pi. So just like before, this is really just like cosine of some junk in here, u or theta, whatever you want to call it, I don't care. And so you want to know what angles, when you plug them into cosine, do you get root 2 over 2. Going back to our trusty unit circle, Cosine is the x-coordinate. Where's the x-coordinate? Positive root 2 over 2. It's going to be here and here. Unfortunately, these two angles are not directly across from each other, so I can't like jump from one to the next to kind of like cut my work in half because it's not equal angles. You know, it's not an equal angle to jump from one to the other. It's always equal if they're directly across from each other, but no go on this one. So we're kind of stuck. So I'm going to have to look at two general solutions. The first one is this angle here, which is the pi over 4. And then the other angle is all the way around, which was 7 pi over 4. So those are my two angles that I'm going to create my general solutions from. So what I need is, I'll separate these two. I'll do them side by side. I need what's inside my trig function, that angle, to be equal to pi over 4 plus any number of rotations. So I need it to be 2x plus pi over 4 must be equal to my pi over 4 plus what? We want to go all the way around, so 2 pi k, good. Now the other one, I want my 2x plus pi over 4 to be equal to the other angle, which was, what, 7 pi over 4? Plus, again, full rotations, 2 pi k. And yeah, the book's using n, right? Oh, well. You know what? For this one, I'll use n's just for fun. All right, there's n. Everyone happy? Just for your own. I mean, be used to it. Books usually use k or n for these trigs. So if you wind up in a calculus class and they're all of a sudden throwing k's around, you're like, what? It's what n was here, or vice versa. So now let's try and solve these generally. This first one, it's actually pretty nice because if I subtract pi over 4 from both sides, it's gone. So I get 2x equals 2 pi n. And then if I divide both sides by 2, I get x equals pi n. Pretty nice. I've solved for x here. Don't forget now, we need to start plugging in some values for n. So let's let n be 0 first. What if n is 0? What do you get? 0. So x is 0. And does that live inside 0, 2 pi? Yep, so we're good. Let n be 1. And you get x is pi. And that definitely lives in 0, 2 pi. And if n is 2, you get 2 pi, which does not live in that interval, right? Because it wasn't open parentheses on that? Yeah. I know you're catching up. Oh. You see why the 2 pi doesn't work? Yeah, because this is a parentheses on the 2 pi. That means do not include. Brackets means include. That's why 0 was okay, but 2 pi is not. All right, so we've exhausted that one. Now we need to do the other general solution. So I will subtract pi over 4 from both sides. And then that leaves me with 2x equals, now 7 pi over 4, take away pi over 4 is 6 pi over 4 plus 2 pi n. I can reduce that fraction, so I'll do it real quick. 6 pi over 4 is the same as 3 pi over 2. And now divide everything by 2. So dividing 3 pi over 2 by 2 becomes a 3 pi over 4. dividing 2 pi n over by 2, the 2's cancel, you just get pi n. Now, because I'm going to have to start plugging in values of n, I'm going to go ahead and put these together now by getting a common denominator, multiplying top and bottom by 4. And that gives me x equals 3 pi over 4 plus 4 pi n over 4. Putting those together, I get 3 pi plus 4 pi n over 4. You can't put those together. You have to wait. So this is our general solution here. Is that okay?
Yeah.
Okay. And now let's plug in some values of n. I'll do it up here. N is 0. You get x is 3 pi over 4. N is 1. You get x is 7 pi over 4. That's still within 2 pi. N is 2. You get x is, what, 8, 9, 10, 11 pi over 4. It's going up by, what, 4 each time? Oh, we're past 2 pi, aren't we? We're past 2 pi. 7 divided by 4 is bigger than 2. Did I say 7? 11 divided by 4 is bigger than 2. 7 divided by 4 was less than 2, so we were okay on the 7 pi over 4. The 11 pi over 4 we're not okay with. No? So we get our total final answer here. We've got 0, pi, 2 pi didn't work. We have 3 pi over 4, 7 pi over 4. That looks like it.